All right, let's do it. So thank you everyone for coming early this morning. Day 2 of NDC Oslo. It's been great so far, yeah. This is my first trip to Scandinavia, so I'm just having a great time. Although I am based in Phoenix, Arizona, USA, where it is a lovely 30 degrees Celsius right now at midnight. It has been a bit cold. But I'm Barry Stahl. I'm a solution architect and developer for Carvana based in Phoenix. And I am the kind of person that keeps a list of his favorite physicists and his favorite mathematicians. So that right there probably tells you everything you really need to know about me. Explains pretty much any behavior you might see. What's he do? Oh, favorite physicists, mathematicians, right. But of course, I also love to talk about such a list. So please feel free to tweet at me, tell me who I left off the list that should be there, who is on the list that shouldn't be there, etc. That's Twitter. So we'll do that. We'll keep that conversation going on Twitter. So besides being the kind of person that does keep such a list, I am also an open source contributor. I have a number of projects that I shepherd. None of them particularly germane to this talk, so I'm not really going to go into any of them, other than to point out that the first one, Liquid Victor, is the one that I used to put together these presentation slides. And this slide is a little more germane for people in the US, but Carvana is an amazing place to work, so if you're looking for work in the United States, please feel free to check it out. I'm also an organizer of GiveCamp. And there are GiveCamps all over the world now. So if you're familiar with it, or if you're not, it's a weekend event where we put a bunch of software creators, that's you guys, in a room with a bunch of great local charities. And we code for the weekend and turn that code over to the charities at the end of the weekend. It's quite an amazing experience, very agile. And as our friend Rob Richardson, who has spoken here in the past, likes to say, he works with me on it, he likes to say that sleep is optional, caffeine is provided. Finally, on a little bit more personal note, before we get into the content, a few months ago, I gave my 100th public talk. And that kind of thing is just not possible without these amazing communities. So all of you for making this community happen, all of the volunteers who actually do all of the work, and I just get to travel around the world and have fun talking to you guys. All the sponsors who make this possible, thank you all, because I would never get to do these kinds of things if it wasn't for this community, and I appreciate every minute of it. So thank you. All right, we're going to talk about algorithms today. We won't be talking about sorting algorithms today, not because they're not cool, just because there's a lot of other types of things out there that we can learn. And we're going to particularly focus on algorithms where we've learned them from nature. Nature has had 4 billion years of evolution to optimize these kinds of things and to figure out what the best ways are to solve problems. You could call it the original genetic algorithm, right? So we're going to talk about some of those. So here's what we'll look at. We'll look at 2 different best path algorithms that come from nature. We'll look at 2 different cost reduction algorithms. We'll talk about what that means and how we can use them by applying one of them to an AI model. And we will use one of those in place of, say, gradient descent or one of the other algorithms that can be used to train a machine learning model. Sound good? All right. So let's start with best path. So this is a simulation I put together of a bee colony optimization. So I'll use this same simulation setup for the next type of best path as well. So what you see here are 20 nodes, and I've arranged them in a circle so it's easy to see when the best path has been found. The best path, of course, for nodes in a circle is just around the outside of the circle. So it's easy to see if we found the best path or not. And then we don't know what the best path is, so we're just trying to find it. So we start off with lines going all over the place, and then we start running this bee colony optimization. And you can see eventually it gets almost to the point of actually finding what is easy to see as the best solution. So how does this work? What are we doing here? Well, there are actually 3 types of bees that we use in a bee colony simulation. The first is an active worker. Then there are scouts and inactive workers. Okay? Active workers, they forage on a known path and a neighboring path. So they do what's called a neighborhood search. They know their path, they know the length of it, and they try a neighboring path. And they check the length of that and they see which one's better. And if it's better, they move to that. Scouts, on the other hand, use a random path. So this is a combination algorithm. This is one where you're using a combination of neighborhood search and random search. So we get some flexibility there. And then finally, there are inactive workers. And inactive workers have a very interesting role. They basically take their starting point from the best path found from other bees. And then they get rotated in. So let's see how that works. Let's see if we can make this thing display well. If I open a new tab. Nope. One more try. Nope, not going to work. All right, hopefully you can see that okay. If not, the slide deck is already up on the internet. AmazingAlgorithms.azurewebsites.net. It's linked at the end. So you'll have these. Also, by the way, on the second slide of each one of them, there is the pseudocode for this, so for each of the algorithms. So you could take that pseudocode, copy paste it in as comments into whatever language you're interested in trying it in, and use that as a foundation for starting to put this together. All right, so what do we do with bee colony? Well, basically what we're doing is we're going to cycle through a bunch of times. We're going to pick some number of epochs, which is the full cycles. There are sometimes better ways to stop. I've kept it simple for this, so we're just going to run n number of times, maybe 10,000 times or something like that. But we could look for like when the solution stops changing. That's another way of, in fact, maybe a better way of trying to tell our algorithm when to stop. Then we're going to loop through each bee that we have. Maybe we'll start with 100 bees, 70 of which are active workers, 20 scouts and 10 inactive workers maybe. And depending on what type of bee it is, if it's an inactive worker, we're just going to ignore them for now. But if it's an active worker, we know the length of their path, they have a defined path, and what they're going to do is we're just going to pick 2 nodes and swap them. And they're going to check that neighborhood. So they're going to check a path that's neighboring to the current path and see if that's shorter. If it is, that becomes their new path. There's one more thing we do at this point. We check and see, compared with all the other bees, did this new path that we found that was shorter, is it the shortest path found so far? And if it is, we get to do the waggle dance. That's where bees go and tell the inactive workers, here's where I found the food. Here's the shortest path that I've found to the food. And those inactive workers have some percentage chance of being convinced, maybe a 90% chance, that that's the best path to the food. And they take that path as their path. So that when they're rotated in, now they start with that as their path and they explore neighboring paths to that. But there's only a 90% chance of them being convinced, or so. You can tweak that value. That means that they may have the previous solution. They may still have a random solution from the very beginning when we start. They all have a random solution. So we get some element of randomness. We get a lot of paths explored. And then, of course, we get our scouts, which are totally exploring random paths at all times. So it helps us not get trapped in what we'd call a local minima, where if we find a fairly short path, but not the shortest path, we might still find the shortest path that's going some other direction because we have these random things being explored and because we're exploring neighborhoods. This all making sense so far? All right. So, bee colony optimization. Well, we have the advantages of it being multiple search types, neighborhood search, random search, and that we propagate the currently best known solution to other inactive workers. There are a lot of things a lot of knobs we can turn, a lot of dials we can twist on this one. We can change the number of each types of bees or the number of bees that we use in the solution. We can change the probability of persuasion. So how easy is it to convince one of the inactive workers that that's the best solution and they should change to that solution that was just found? And also how often we swap out active workers for inactive workers. We can tweak all of these these features. Now these algorithms are nice because they're not that, they're the scale, you can scale them out to huge problems and they can still find usually a good enough solution. But unlike algorithms where you're doing an exhaustive search where you're checking everything, you can never be guaranteed optimality. So we never know for sure that we find the best solution. But of course, if it's an exhaustive search and the problem is huge, we'll never finish either. So we'd never be guaranteed optimality there either. Sound good? Want to check out ant colony optimization? All right. Same simulation. We've got those 20 nodes around the outside. We're trying to find the best path. You can see that this one doesn't get as good a solution in as many epochs as I allowed it to try. And this is a completely different type of search algorithm. So in this case, we're basing everything on pheromones. So if you've ever gotten ants in your house, I don't know how big a problem that is here. In Arizona, certainly, if you get ants coming in your house, you have to stop it right away. You have to do something immediately because they lay down pheromones as they walk. And other ants can follow that path. So if you get a few ants coming on a single path, you're going to get a lot more. So we use this to optimize our search, and ants use it to optimize their path to their food. Because the more a path has been used, the more pheromones are left on it, which means it's more likely that other ants are going to take that path. So we're going to explore an example of that. So this is the flowchart for ant colony. And again, like the other one, we have pseudocode there for it that you can check out and use if you wish. For ants, all we're really doing, we're only going to have a few ants, like we're going to have 4 ants. And we're going to loop through each of those ants. We're going to put them in random places so they can start in random places because this is we're making a complete traversal. We have to get to all 20 nodes. So it doesn't really matter where they start. The path is going to be the same regardless of where you start. So we put them in random places and then allow them to start exploring. And so each ant moves one node to the next. And the way it makes that decision as to which node it goes to next is based on the amount of pheromones. So it's proportional. The probability of it taking that path is proportional to the amount of pheromone left on that path. So at the beginning, we probably have no pheromones anywhere when we first start. So it means it's an even probability, equal probabilities of going to any of the other 19 nodes in this solution. As we go, though, as they march on, if you will, they leave pheromone behind them. And the interesting part is that the pheromone dissipates. So the amount of pheromone gets weaker over time, which means the longer it takes for them to go out and finish their circuit, the more pheromone has evaporated. So the longer the path, the less pheromone is left on the path. You see where I'm going with this? Right? So the shorter paths will have more pheromones left on them at the end of each epoch, which means they're going to be more likely to be taken by the next ant or them. So that's the gist of it. So we keep doing that, we keep looping through, and eventually we're going to start getting a bunch of pheromone built up on these shorter paths. Now we have to have some kind of calculation that tells us how to reduce the amount of pheromone. So that's going to be one of the things we can tweak, is how fast does the pheromone dissipate? And we'll have to calculate, at the end of each circuit, we're going to have to calculate how long was that path, and then inversely proportional to that, we'll have to remove some pheromone from that to simulate the evaporation of the pheromone. It's actually kind of a fun one to implement. If you want to explore best paths, I do recommend starting with this one and playing with it a little bit. It's kind of fun. Now, of course, it's easy to get stuck in a local minima on this one, because you can see, as you start getting, one path having a lot of pheromones, it's going to start converging on that, because more ants are going to take that, and you're going to kind of snowball. So you can get caught in a local minima, so you want to be careful about that. You want to have a method for handling that. Maybe it's just run the full simulation multiple times with, starting in random places, because there is an element of randomness, a significant element of randomness to this. And like the bee colony, it is not guaranteed to be optimal because it's not an exhaustive search, but it is also, it scales pretty well. You're not going to exhaust your computing capabilities because you tried to exhaustively search an untractable problem. All right. Let's take a look at ways to reduce costs. Now, costs, remember, in this can be money, but it can also be time, it can be expenses, it can be error. And we'll look at error here in a little bit. For the two examples, we're going to use this function. This is the Mikhailovich function, and it's used basically to test these kind of optimization routines, because they have that deep blue dip in the middle there. That's our minimum. That's our minimum point, and we want to find that point. But there's other local minima that we could get caught in, so we have to have ways of dealing with that. So what you're about to see here is a simulation of Firefly optimization. So this is a swarm of fireflies that are trying to find the best solution, and they're swarming to the brightest other fireflies. So they swarm towards each other, depending on how bright the other fireflies are. And the brightness of a firefly is directly proportional to the quality of the solution, meaning the lower the cost, the brighter the firefly, the more other fireflies swarm to it. This one's a fun one, too. So what we do here is we start by scattering a bunch of fireflies out randomly. And we can use, I think I used 40 in this scenario for this size problem, but you'll scale the number of fireflies to your solution. And then we loop through each of the fireflies, and we loop through each pair of fireflies. So for every combination in that Cartesian product of the two fireflies, for each pair, which one's brighter, how much brighter is the other one relative to that one, and then how far apart are they? And then we move the dimmer one towards the brighter one. It's the easiest way to equate it is the law of gravity. It is directly proportional to the brightness, or the mass in terms of gravity, and inversely proportional to the square of the distance between them. So the further apart they are, the less attractive they are to each other. The brighter they are, the more attractive. And we move the dimmer one towards the brighter one using that kind of equation. It's actually a lot simpler than it sounds. And what ends up happening, as you saw in the simulation, pay attention to the red dot there. What ends up happening is that red dot is representing the firefly that has the best solution right now. So that's the brightest one. So when it looks like it's jumping around, it's not that a firefly is jumping, it's that it's changing fireflies, because that other firefly found a better solution. So they keep swarming towards better solutions. But they're not just swarming towards the best one. They're swarming towards other brighter fireflies too. So they explore a lot of the area towards the best solution. So you get a lot of coverage, especially as you get closer to the best solution. But like all optimization algorithms, they have it has its difficulties. For one thing, it works best for linear problems. So you can kind of picture it if you think about the simulation. If it was a discrete problem, if it was problems where only integer values were usable, it would be hopping around and it wouldn't really be good at it. It doesn't have a good space to explore. Where if it's a linear problem, so you've got an infinite number of values to explore, it does a really good job of exploring that. There are better solutions for integral problems, for discrete type problems. And of course, optimality is not guaranteed again. With this one, we have another interesting problem, and that is it can suffer from sparseness. Think about this. If I were looking to find the densest matter in this room, and I scatter a bunch of fireflies around, well, there's a lot of matter close to the floor and the stage and what have you, but there's not a lot of matter up in this area up here, up higher. So if a lot of my fireflies end up there, we might have a tough time finding that all the matter is lower, right? Probably the thickest is this skull. Anyways. And then think about that, say, in this kind of scenario, where if we're trying to find the densest matter there, what are the odds, no matter how many fireflies I scatter about, because this space is so sparse, what are the odds of us actually finding some level of density of matter? And then it gets worse and worse as you add dimensions. So now if I add time onto this as a dimension where I have to think about that, now there's hardly any point in that four-dimensional space-time, say words, in that area where there is actually dense matter. So it can be very, very hard with this type of algorithm to actually find a good solution. Something you have to consider. All right. Last one. Let's talk about the amoeba. Amoebas forage for food, and they do so with using an algorithm, if you will, that they have used for billions of years now. I don't know when the amoebas came around, but I know it was a long time ago. So what you're going to see here is a simulation of an amoeba with that I used with three points. So it makes a nice triangle, makes it easy to see how it moves about. And we're simulating the foraging behavior of an amoeba. Amoebas look for, protein-rich or carbohydrate-rich. I think it's carbohydrates. They look for carbohydrate-rich environments, and then they surround it, and they contract on it, and then utilize it, I assume. So we're going to search for our best solution using a method like this. Now, I said I have 3 points on the amoeba here. You can use arbitrary numbers of points. In fact, I would recommend, depending on the number of dimensions in your problem, that you use more points on your amoeba than you have dimensions in your problem. But this one's a nice, simple-looking flowchart. There is a significant calculation here, and we'll get to that. But primarily, all we're doing is we're randomly starting, putting our random 3 points, see which one's best, and then we move the amoeba around in a way that's defined by this simulation of their foraging behavior, and eventually contract on the solution. So here is the interesting part of this one. What you can see here is that we have an amoeba with 3 points, and then we have a centroid. So there's the one on the left is the best solution found so far. Okay. The other 2 points are less They're less carbohydrate rich, right? They're not as efficient. So what we're going to do is we're going to find a centroid, the point between the two other solutions. And if there's more than two, it's still the average point between all the other solutions, okay? That's our centroid. We're going to draw a line between the best solution and the centroid, and then we're going to pick 3 points on that line. We're going to find the best solution for those 3 points, and then we're going to move the worst solution, the worst point on the amoeba, to the best of those new 3. Those 3 points are the, what is it called? The contracted, reflected, and expanded. So the contracted is the median point between the best solution and the centroid. The reflected is you reflect that across, and then the expanded is you double it out. And one of those 3 points is likely to be better than the worst one you have so far, and you move that worst point there. And that's how the amoeba moves around. Now, what do you do if all of those 3 points are actually worse than the worst solution you have so far? What we hope that means is that we've surrounded the best solution already. And at that point, we need to contract. So then we contract the amoeba and see if we're condensing on the proper solution. So, amoebas are a neighborhood search, right? It's searching in the area based on that centroid. We surround the solution, we contract on it. There's a number of things we can tweak. We can tweak the size and the number of points of the amoeba. And we can also affect the number of executions, so we want to look out for those local minima. And again, optimality is not guaranteed, and it can suffer from sparseness. If it simply cannot find, as far out as we've tried it, it can't find points where there's good solutions, it's going to have trouble. So we're going to want to probably run it a number of times. Cool. So we've got these algorithms. What can we do with them? All right, let's get a little background here. We've got some data, and it's clearly linear data, right? I mean, that's pretty obvious that it's linear with some noise, but there's definitely some linear data there. If we want to predict one of the points on that line based on the other, so if we have the x-axis value, and we want to predict the y-axis value there, we can do a simple linear regression, right? Excel does that for us. So we'll draw a best fit line. All we're doing there is we're figuring out how we can predict y knowing x. There's another way we could do that. We don't need to do it this way, but there is another more interesting way of doing it, and that's with a machine learning type model, where it's the very simplest of these models. It's only got one input and one output. The input is x, the output is y. And between them, it has a single edge. So edges in machine learning models have weights. So we have to figure out what the weight is of that edge. And output nodes, calculated nodes, have a bias. So on this chart here, I've called the weight M and the bias B. And we have to figure out what those are. And so if you think about the letters that I chose there, you might see that those were intentional, because what we're actually looking for when we make that prediction is we want to calculate y. So y is equal to, we multiply the weight times the input, m times x, and then we add in the bias, plus b. Y equals mx plus b, as we all remember from first year algebra, is of course the equation for a line. So all we're doing when we find m, the slope, and b, the offset, we're finding the values that minimize the error in that line. And whatever minimizes that error, that's our best fit line. right? I'm seeing some head nods, so I'm feeling pretty good about this. If we look at the error function here, you can see that it varies greatly with the slope, which totally makes sense, right? If we have the slope opposite of, opposite what of the actual data, it's not going to fit at all, and we're going to have a huge error. But as we get the slope right, it comes down to the V, and it's hard to see in this. You'll be able to see it when you have it locally, but there's actually another V in the trough at the bottom there, and that's where we have, that's when we're adjusting that bias. As we get that bias right, as we move that up and down, we find our best fit line. So our error is then minimized. So that's what you're doing when you train an ML model, is you're finding the minimum point on the error function graph. We can do that with much more interesting things. So let's take a different model. This is a model that I built for predicting the political party of a vote of US Congress members. So this data is from the 80s, back when it was a lot harder to predict what people were going, what party they were from based on their votes. But as we'll see later, wasn't all that hard even then. So what we have is, we have data that had about 430 data points or so, 430 different votes, 430 different Congress people. And each of them we have the data for 16 votes. So the 16 bluish boxes or bluish circles on this graph represent the inputs, so the votes. So how did they vote on each of 16 issues? Each of those has an edge connecting it to the output. Each of those has a weight. And then our output node has a bias. So we've got 17 different values that we have to calculate. We have to figure out what they are so that we minimize the error when we plug in those votes. We want to minimize the error of the output value, and the output value is either a 0 or a 1, depending on whether they are a Democrat or a Republican. We still only have 2 political parties in the US. I don't know why that is, but actually some would say we only have 1, but a different subject altogether. So if you can see it here, there is actually an equation on this. So the equation is how we calculate that output node. The value of the output node is the value that goes into the first node times the first weight, plus the value that goes into the second node times the second weight, plus the value that goes into the third node times the third weight. So V1 times W1, V2 times W2, V2, all the way up to 16. And then we add in that bias. And then we do one more thing. We add in what's called an activation function. An activation function just takes all of those range of values that we can get and turns it into a 0 or a 1. So in this case, we're going to use what's called a sigmoid function. Any values less than -5 basically go to 0. Any values greater than 5 go to 1. And there's this nice smooth curve in the middle that makes it a 0 to 1 value. So we end up with that output node having a value of somewhere between 0 and 1, depending on what we calculated for it. And we want to minimize that error. So we want to find the values for those weights and that bias that minimize that error when we try all that data in there. That's what it means to train a machine learning model. So let's look at some code that does this. Let's jump into Visual Studio here. I'm a C# developer, so I do most of my work in Visual Studio. And this is the main program. And this code is all up on GitHub, so you'll be able to pull it down. It's linked in the slide deck at the end. And you can see what we first do here is, the first thing was we split the data. So we take 3/4 of it, that's going to be our training set, and then we're going to reserve 25% of that as our test set. And we're going to use that to test to see how good our training was for that particular instance. Now, you'll notice I did that here outside the loop. So I'm going to only have one training set and one test set, and I'm going to keep trying this a bunch of different times, but I'm going to use the same training data and test data each time. The reason I did that here is because it's faster and it didn't seem to make a difference for this problem. Other problems, it may be better to try different training and test data inside the loop. You'll have to experiment with your own particular problems. So we're going to loop a bunch of times and try this thing out. And what we're going to do in those loops is we're going to train and test. So we're going to train the model, and then we're going to test it and see how good it is. And then we're going to look for the highest accuracy. So did this training test cycle, when we tested it, did it come out better than others? If so, we're going to hold on to that one. And that may be the one we end up using. And then, of course, we update a bunch of statistics so we can see how well we're doing. So let's drill into this train and test model method that you see here. And you notice we send in two things to that, the training data set and the test data set. So what do we do with that? Here is our train and test model method, and of course all we're doing is we're training the model, but we send into the train method, we send in three things. The training data set, that makes sense. We also send in our error function and our activation function. So that's that sigmoid function that we saw the graph of earlier, okay? So we're gonna send those three things into the training set. Then we test it, all we have to send in is the test data because we've already trained our model at that point. We already know what all those values are. So now we just try the test data using the predict method, and we'll see that later, to see what predictions it makes and how accurate those predictions are. In other words, when it predicts for, Congressperson A that they're a Democrat, were they or weren't they? And if not, we have error, and we have to take that error into account. So let's drill into some of these other things. Here's our error function. So the error function is just the sum of the squares of all of the errors for all of the data points. So we try every data point, and every congressperson, and then whatever the value, the calculated value is, remember we can calculate a number between 0 and 1. If it was supposed to be a 1 and we got a 0.7, the error is 0.3, we square that, we add that all together and square it, and that's our total error. So we're going to need that. We're also going to need our activation function, and we've got three different activation functions here. The one we're using is Sigmoid, that's at the bottom, but I've also got two others in there, the no activation function, the one that just allows it to be any value it wants, so whatever value it gets, it returns. The other most common one is called ReLU, rectified linear units. That basically is, it just chops it off at 0. So if it's 0 or less, the value is 0, otherwise it can go on to infinity in the positive direction. Now, the advantage of ReLU is that it's really fast. Very simple function. So if you have a ton of data, you may be better off using something like that and running all that data lots of times and maybe sacrificing the quality of the activation function a little bit in order to be able to run the data more. In this case, I don't have a ton of data, so I don't mind using the slower but kind of cooler looking function. Maybe more accurate. All right. So those are our error function and our activation function. And this is what our model looks like. So when we're training a model, what we're doing is we're calculating the weights and bias. So at the bottom here, you can see that this has an array of weights and a bias. And the array of weights is going to be an array of size 16. But we also hold the activation function here in this model. And we'll pass this model around and be able to use it to train and test our data. So here is the first time we're actually dealing with an amoeba. All of that previous stuff was kind of specific to the solution. It was specific to our problem of trying to figure out who's voting how and what their political party is. Now we're going to start training our model. And so to train it, we have to have that amoeba, and it's got to do its work of solving that problem of minimizing the error in our model. So in this is where we configure the simulation itself, and you can see here I have an amoeba size of 13 for this one, which I'm not really sure why I picked 13, because I really probably should have picked 18, since we have 17 dimensions to this problem, right? 16 weights and 1 bias. I've also got a max epochs in here of 70, and then there's some other values that we can play with, but I couldn't tell you exactly what they do. Then below that, we have our objective function. That's the thing we're trying to minimize. So it takes both the voters, the list of voters, and it takes our activation function. And then what we do with that is we configure the new organism, that's our amoeba, and we use its solve method. And the solve method, what it's doing is that flowchart we saw earlier, where it's just looping through and moving the nodes around to try and minimize that error using the error function. All this code, like I said, is out there for you to explore and play with and figure out how to make it better. Happy to take pull requests, by the way. If you figure something out and make it even better, love to add that to it. So here is now our predict method. Once we've got the model fully trained, once we've minimized the error and we've said, all right, this is the model we found, the set of weights and bias, set of weights and the bias that minimizes the error function. Now we can use this predict method. So we pass in a voter's votes, those 16 votes, and it comes back with a value. And it says this is either a Democrat or a Republican. So in this case, I just arbitrarily chose greater than 0.5 is a Republican, less than 0.5 is a Democrat. Doesn't matter which is which as long as you're consistent with it. And what it returns is the result, so Democrat or Republican, and a score. And the score in this case is just the actual value that we calculated. So if we got a 0.8 out of it, then we're going to say, well, that's a Republican. But we know that's not all the way, right? A perfect score for a Republican would be 1. A perfect score for a Democrat would be 0. But we only got 0.8. So it gives us sort of a probability. It tells us how certain we are that that value is accurate. Cool. So let's run this program, sort of. And what we end up with is a display like this. You can see at the top that we have some statistics. And what we found here is that our best model was 95.7% accurate. Considering we only had 400 data points to work with, that's really amazingly good. And what that tells me is even back then, it was pretty easy to predict what party someone was from based on their votes. And then taking that model that was 95.7% accurate, if we run it against all of the Congress people in the list, so run it against the entire voter list, here are all of the incorrect votes and the values that they had. So not many failures, but the failures seem kind of extreme. Like we have the very first one is a Democrat, and it was 99.98%, if you will. The value was extremely Republican. So maybe that person is an outlier and really voted like a Republican, or maybe our model is just not really good at the way that person voted, at handling that. So always interesting to explore these kind of things in your problem and see, is there outliers in the data? Could you clean the data up and make it look better and make the model more accurate? This is fun stuff to play with. Wouldn't necessarily recommend doing this yourself because there's really good tools out there to train machine learning models, but we can. And when we're in situations where there isn't something that works well, or if there's a situation where our problem is so huge that the typical tools don't work well, we have these at our disposal. All right. There are some more algorithms that are Bioinspired that I enjoy talking about, some of which I really don't want to try the roach infestation one. I don't know, there's just something creepy about that one. But there are lots of things like particle swarm optimizations and bacterial foraging and such. I do an entire talk, in fact, a couple of different ones on genetic algorithms, because those are super fascinating. And as I mentioned at the beginning, all of these talks you could say are genetic algorithms themselves. The hard part about genetic algorithms is actually defining the problem. It's setting up the model in a way that where you can describe the options in the problem as if they were DNA. I do one where it's I train a model to play a game of chutes and ladders or snakes and ladders. I don't know what you call it here, but it's a kid's game. It's actually one where you don't really get to make a decision if you're playing the real game, but we play it like you get to choose, do you want to take a ladder or slide down a chute or not? And then it has to figure out what's the best strategy. And I describe each of those moves, each of those possible moves as DNA, and then allow the organism itself to figure out what's best and the best solutions survive. Really interesting stuff. All right. So, what have we done today? We've minimized some costs, and you saw that we used that to train an AI model by minimizing the error function. We did the Firefly and the Amoeba methods for minimizing cost. We also did a couple of best path algorithms, so finding the shortest path between points. I didn't talk much about it, but shortest path algorithms are kind of interesting. I mean, it's mostly a solved problem if you think about mapping, but it's used a lot in video games, right? You have your pathing algorithms to figure out what's the fastest way to get from this point in the world to the next point. So I see that kind of thing a lot in video games. But the best algorithms that we use today are like, you'll see the term A-star, A-splat, whatever, A-star algorithms. Those are exhaustive searches. So if you have a huge space that you have to explore, it can take a long time to figure those out. A-star is actually, it's not entirely exhaustive. It's exhaustive up to the point where you can prove that you going any further doesn't help you anymore. You can't possibly get better. So super interesting stuff. I encourage you to explore some of these things because they're definitely interesting. All right, so some resources. As I mentioned, this slide deck is available right now on the internet, amazingalgorithms.azurewebsites.net. My blog is Cognitive Inheritance. I don't blog a lot, but when I do, I'm very wordy about it. So there's that. And I do talk about some of these things on there on occasion. I do have some other talks that are on YouTube that are about this kind of subject. There's one in particular that is interesting in the same kind of way as this talk, and that's the Building AI Solutions with Google OR Tools. So that's OR Tools is operations research. So that's the minimum cost type functions, finding the lowest cost. A number of articles from MSDN magazine where they talk about algorithms like this. I think those are actually the four for these four algorithms that we talked about today. And then there are two sets of code that I want to point out that are linked in here. The bottom one is the code to this that includes this demo. So my AI demos that include this algorithm, this optimization. And then right above it is the algorithms, which is a GitHub repo that is just a shared repo, all languages. Any algorithm you can think of is probably implemented there. And if it's not, you should do that. You should implement it in whatever language you prefer and contribute it. And there's lots of people that contribute to those things. I have contributed several to the algorithms, so I encourage you to check that out and experiment with it. And with that, looks like we have about 10 more minutes, so I'm happy to answer any questions that I can.
I have a question.
Yes?
So there is obviously a number of interesting algorithms, but the big problem I have is how do I choose one?
So the question was basically, how do you choose an algorithm out of all these amazing algorithms that we have? And really the best answer is, it's not going to be a very satisfying answer. The answer is you experiment with them and you try it and you see what works. Whenever I'm implementing anything, the very first thing I do is I implement what's called a naive solution. Think of the simplest thing that you can possibly do and implement it that way, even though you know it's going to be completely stupid, right? It may take forever or it may not find an answer or whatever. But first of all, what you do with that is you learn about the problem. You understand the problem better. And then it gives you a target. If you're building something else and it doesn't even do as well as your naive solution, you know you don't need to explore that option anymore. But yeah, you're going to basically have to research and figure it out. Now, some of the tooling that we have today, like if you're looking at some of the Microsoft tooling within Visual Studio, for example, for training ML models, what it does is it tries a whole bunch of different ways to optimize it and see what works best. So everything that they have built into Visual Studio built into their DLLs that they ship with Visual Studio, they just try them all and see which one works best. And that's really the only good way to do it, other than to have some intuition of which types of models are going to work best for which types of problems. Sorry that I can't give you a better answer than that, but if there was one, we'd all be doing those things.
It's an optimization problem, so you can run it anytime.
If we had a genetic algorithm that would try and, yeah. Mm-hmm. What else? It's hard to see, so. Yes?
Did you use ML.NET framework?
I've used ML.NET.
For this one specifically?
No, not for this. So this was all done in just pure code. So it's straight up C#. Everything that you saw on the screen and you'll see in GitHub is just plain C#. So the part where you would have normally used ML.NET here was done by the Amoeba optimization routines that are in there as well. Yes?
Python has a lot of tools to work with data science and AI. I just wonder, is there anything similar in C#? I tried to look for libraries that does machine learning and data frames and things like that.
Okay, so are you coming from the Python world? Is that what you're?
Unfortunately, the last 2 years. But
Okay.
before that,
So you're looking at what Python-like algorithms or tools are available in C# to do machine learning, and really the best one is probably ML.NET. Yeah, that's Microsoft's implementation, and it does a lot of work for you. So if you have Visual Studio, there's a how do you get it? Do you have to use it as not a plugin, but an extension, something like that? And it will actually, if you give it a data set, it'll do a lot of that work for you to figure out what's the best algorithm, how should it tokenize it. A lot of that kind of stuff is handled. Anything else? Well, cool. I was happy to talk to you today, so thank you very much.